starting today we are having first of a series of lectures on finite element method. What I will first do is I will first give the basis that goes behind this finite element method, and then we will take specifically one dimensional, two dimensional and three dimensional analysis in finite element using finite elements. First let us do a quick recap of some of the solid mechanics fundamentals that you have done earlier. In terms of notation, if you have any three dimensional entity and in that there is a point P given by x, y, z, then the deformation at this point P, that is a vector u, that will be consisting of three deformation, that is u, v and w, okay, and we will represent it as a column vector. So if you have a column vector u, v, w, that will be a notation we will use for the deformation at any point P. Okay, so this deformation vector u will have three components: u for deformation in the x direction, v for deformation in the y direction and w for deformation in the z direction. Similarly, if there is a force field, okay, that force field will represent by fx, fy, fz, that is again a three dimensional vector which will be again a column vector, and this force field is essentially the force field in an object, and this will be force per unit volume. Okay, that means that force per unit volume acting at each element in this body, that is what we refer to as a force field. Okay, then if there can be some tractive forces on the body, okay, these tractive forces will represent as Tx, Ty and Tz transpose. Now these tractive forces, in the case of a three dimensional body, they are the forces per unit area acting on the surface. Okay, if we have any three dimensional object, we can have a volumetric force that will be force per unit volume, typically something like gravity or magnetic forces or something like that. On the surface we can have pressure fields, or we can have a uniform distributed load or similar force fields acting on the surface. These will be called tractive forces, and we can have point forces. Okay, if you have a point force, we will represent point forces by the vector Px, Py, Pz transpose. Okay, this would be the vector, we will refer to that as a P vector or the point force vector. Okay. Then if we talk of the stresses will represent by the stresses will consist of 6 components, 3 stresses: sigma x, sigma y, sigma z, and tau yz, tau xz, tau xy as the shear stresses. Okay, so this vector would represent the stresses. And similarly, if we talk of the strains, the strain will be represented by epsilon x, epsilon y, epsilon z, lambda yz, lambda xz and lambda xy. Okay, instead of representing stresses and strains by a 3 by 3 matrix, we will represent them by a vector consisting of 6 terms. Okay, the 3 stresses strains epsilon x, epsilon y and epsilon z, and we will have the shear strains lambda yz, lambda xz, lambda xy. Okay. Now these strains epsilon x, if you remember how is epsilon x defined, this is the same as del u by del x, okay, where u is the deformation in the x direction. Okay. Similarly, epsilon y, that is the same as del v by del y, and epsilon z is the same as del w by del z. Okay. Then the next term is lambda yz, and this lambda yz would be the same as del v by del z plus del w by del y. Okay, the next term is lambda xz, that would be the same as del u by del z plus del w by del x. Okay, the last term which is lambda xy, that would be del u by del y plus del v by del x. Okay. So the strains can also be represented using these partial derivatives. Okay. So this term is here, this term is here, and this term is here. Okay. Then if we consider any elemental volume, yes, solid, if we consider a small elemental volume, and for this elemental volume dV we write down the equation of equilibrium, then we will get a set of 3 equations which will be given by del sigma x by del x plus del tau xy by del y plus del tau xz by del z plus fx is equal to 0. This you must have done in your solid mechanics. You are taking this elemental volume, finding out the forces acting on all the faces. Okay, for instance, because of the stress sigma x, there will be force acting in this direction. Because of shear forces, there will be force acting in these directions, and so on all the faces. Plus, there will be elemental body force. If I write down the equilibrium of all these forces in the x, y as well as the z direction, I will get 3 equations of this form. This is one. The next would be del tau x y by del x plus del sigma y by del y plus del tau yz by del z plus fy will be equal to 0. Okay, and the third one will be similar, it is del tau x z by del x plus del tau yz by del y plus del sigma z by del z plus fz will be equal to 0. Yeah.
In all these equations, the force sign be negative because the external force should be equal to the stresses.
No, the signs will be taken care of by the direction that we are choosing as this thing. Okay, so the magnitude can be negative, but because of sign convention we are choosing, we are getting a positive term. Okay, so there are 3 equations we get from equilibrium, okay, in a elemental body element, okay, or in a cubical body element. Okay. Similarly, if you take a element which is on the surface, okay, if an element is on the surface, it will look like this. Okay, if you have a 3-dimensional surface, a curvature, and we are taking an element which is on the surface, it will not be cubical, but it will be somewhat pyramidal element like this, or a tetrahedral element like this. Okay. If you consider an element of this shape and we write down a similar equation, now the equation will be slightly different because on this surface we will have the attractive forces, and those attractive forces will be in a direction given by Tx, Ty, Tz.
This is a corner point?
Yeah.
This is some corner point? Or
If you have a body like this,
yeah.
Okay, and I take any element on the surface. This is a point on the surface. Okay, or this is an element on the surface rather. Okay, if I taken a complete element, it would have been something like this in a two dimensional sense, or in a 3D the element would look like this. Yeah, I am cutting it by a curved surface, that I am approximating by a plane like this. Okay, if I write down the equations of equilibrium for this, what we will get would be something like this: sigma x nx plus tau xy ny plus tau xz nz will be equal to tx, and tau xy nx plus sigma y ny plus tau yz nz will be equal to ty, and tau xz nx plus tau yz ny plus sigma z nz will be equal to tz. Okay, so these will be the other three equations of equilibrium in the case of this element. Okay, these derivations you must have done in your solid mechanics courses. Okay, we will be using some of these equations when we come to the finite element method. Okay,
Traction forces are per unit area.
tractive forces per unit area. Okay, the next set of equations, let us say if we are talking of the strain epsilon x, and we want to express the strain in terms of the stresses, epsilon x will be equal to sigma x divided by E. Okay, the E is the Young's modulus minus nu times sigma y plus sigma z divided by E, where nu is the Poisson's ratio. Okay. Similarly, we will have equations for epsilon y and epsilon z. Okay, so for instance, epsilon y would be minus nu sigma x by E plus sigma y by E minus nu sigma z by E. Okay. Similarly, you can write for epsilon z. If you consider lambda xy, lambda xy will be tau xy divided by g, where we can show that g is equal to E divided by 2 into 1 plus nu. Okay. Now, for any three-dimensional object which is subjected to a set of strains and a set of loading, the potential energy in this object, that is the total potential energy pi, this potential energy is equal to the strain energy plus the work potential. Okay, this will strain energy will be using a symbol U plus the work potential WP. Okay, and strain energy, if I say pi is equal to U plus WP, the strain energy would be half of integral of sigma transpose epsilon dV, volumetric integral. This is U. Okay, that means if we take the stresses, multiply the transpose of the stresses with the strain vector and integrate that over the volume, then or half of that will be the work the strain energy, and the work potential, okay, that would be minus of integral of U transpose F dV minus surface integral of U transpose T ds minus sum of all Ui transpose Pi. Okay, I going from 1 to n. This work potential is essentially the work that would be done against the forces that are acting. So if there is a, let us say a body force, this is my object and there is a force field here like this. If this object undergoes the deformation and it gets deformed like this, then in carrying out this deformation we have done a force against this force, that is this component. Okay, so at each element inside this body the work done will be U transpose into F, work done per unit volume. Okay, U transpose is the displacement, F is the force. Okay, the product of force and displacement will be the work done per unit volume. This force is per unit volume multiplied by the volume of this element and integrated over the complete element. Okay, similarly this will be the work done at the surface. If there is some load at the surface, then in carrying out this deformation whatever work is done against these forces, that is expressed by this term. And if there are some point loads, then whatever work is done against these point loads, that is expressed by this term. Okay, so this is the expression for the work potential, this is the expression for the strain energy, and the potential energy is the sum of these two. Okay. Is that all right? Any question up to this point? Okay. Now
aren't we taking strain energy into the work potential into account in the work potential equation?
the strain energy, no?
Because work done against deformation, I mean work done for it to get deformed. That is the first term of the work.
No, work potential is the work done against the external forces. Strain energy is whatever energy retained inside because of the strains in the body. Okay, the two are because of two different terms. And the sum of the two will be the total potential energy. Okay, if you have an object, you keep it compressed, there are strains inside the body. Okay, there will be some internal forces which are causing those strains. So they will cause some potential energy. Okay, that is the strain energy part of it. The work potential is that in holding this, I have applied some forces from outside. Okay, so that is the work that has been done from outside. Okay, so that part is the work potential. Okay. Now, if you look at these equations, these express the strains in terms of the deformations U, V and W. Okay. Similarly, we have expressed here strains in terms of the stresses. Okay, so if I know the deformations, I can get the strains from here. Once I know the strains, then using these equations I can get the stresses. If I know the strain, I can get the stresses from these equations. Once I know the stresses, then I can get the potential energy from this equation. Okay, because if I know U, which is the deformations, if I know U, I can find epsilon. If I know epsilon, I can find sigma. Okay, and I know the loading T and PI's and the F's. Okay, so basically, if I know the deformation, I can find out all the other terms in this, and thus I can find out the total potential energy. Okay, so from U I can get epsilon, from epsilon I can get sigma, and once I know epsilon and sigma, I can get the total potential energy pi. Okay, so if in any object, to find out the total potential energy, all that I need to know is an expression for the deformation vector U. Okay, if I know this deformation vector U, I can compute the total potential energy. Okay, and in a finite element approach, what we basically do is we try to get an expression for this vector u. Okay, for instance, if I have a simple one dimensional element or one dimensional object like this, okay, maybe I will say that the deformation in this u is given by a0 plus a1x plus a2x squared. That means I will say that this deformation as a function of x is given by this. Once I know u, I can calculate epsilon, I can calculate sigma, and I can calculate the potential energy. And then I know that in equilibrium my potential energy will always be a minimum. Okay, for stable equilibrium potential energy is always a minimum. Okay, so if I assume a displacement vector like this, okay, if I assume that the deformation at any point is given by this equation, I can compute the potential energy using this expression. Okay, and this is the basic approach that is used in the finite element method. Okay, we have this set of equations, we will use this set of equations to express pi or the total potential energy as a function of u. Okay, and our aim is to find out u. If we can find out the deformations, we can find out everything about the object. Okay, so we will just see how we can find out the deformation in objects. Okay, the first method for doing that is what is referred to as the Rayleigh-Ritz method. Okay. To explain this method, let us take the same case. If you have an object like this or a beam like this with a central loading, okay, let us assume that the deformations in the vertical direction are given by this equation. Okay, this equation may or may not be correct. This is only an assumption to start with. Okay, in fact, from your solid mechanics knowledge, you will probably know that this equation is wrong. Okay, because the deformation in this will not be a quadratic expression like this. Okay, but right now we are just making an assumption which may or may not be correct, that will come to know later on. Okay, so if we are making this assumption, at this point we have x is equal to 0, and at the end let us say we have x is equal to 2L. Okay, where L is the half length of this rod. Okay, this beam is fixed at the two ends, so one of the boundary conditions would be that u at x is equal to 0 will be equal to 0, and u at x is equal to 2L will be equal to 0. Okay, if you use this expression, put it in this, what we will get would be a0 will be equal to 0. Okay, at x equal to 0, these two terms will become 0, u is given to be 0, so a0 will be equal to 0. Now we put x is equal to 2L and then u is equal to 0, so what we will get will be 0 will be equal to a0 is known to be 0 plus 2L into a1 plus 4L squared into a2. So from this we will get a1 will be equal to minus 2L a2. Okay, so if we put this back over here, we will get an expression for u which will be in terms of a2 and it will be x into A2 into become x minus 2l. I have put this and this into this equation. Okay. Now, in this method, so far what we have done is we have assumed a distribution for u, okay, and we have assumed this distribution u in terms of the parameters a0, a1 and a2. Okay, so in this distribution there were 3 parameters a0, a1 and a2, okay, and then we have ensured that the boundary conditions are met. These are the boundary conditions. We have ensured that these boundary conditions should be met. Okay. So, the first step in the Rayleigh-Ritz method is what we say, assume a set of functions which are given as, let us say, phi I of x, y and z, okay, such that u is equal to sigma ai phi I of x, y, z, v is equal to sigma, let us say, aj of phi j x, y, z, and w is equal to sigma, let us say, ak of phi k x, y, z. Okay. For instance, in this case, I have assumed that u is given by this expression. In this expression, we have a0 plus a1x plus a2x squared, okay, which is the same as this. Okay, so my phi I is, my phi 1 is 1, phi 2 is x and phi 3 is x square. Okay, I will write it here, phi 1 is equal to 1, phi 2 is equal to x and phi 3 is equal to x squared. Okay, so my u is given by an expression, by a combination of 3 phi i's which are 1, x and x squared, and my constants of these parameters ai are a0, a1 and a2. Okay, so in general I will write down u, v and w in using similar expressions like this. Okay, I can assume it to be a quadratic function, I can assume it to be a higher order function, or I can assume it to be consisting of some other type of function. Okay, so I will assume that the deformations will be given as some function of x, y and z. Okay, essentially what I am doing is, whatever my solid be, throughout this solid I am assuming a deformation field given by this. I am assuming that at any arbitrary point the deformation u, v and w, this deformation will be given as a function of x, y and z governed by these equations. Okay, so we are starting with this assumption. As I said, this assumption may or may not be correct, we do not know at the moment. Okay, the first step in the Rayleigh-Ritz method is to start with a set of assumptions like this. Okay, and as a result of this, this u vector, okay, this becomes a field. Okay, it becomes a field, meaning it is a function of x, y and z. Okay, and this function of x, y and z will be governed by these parameters a0, a1 and a2. Okay, it becomes the field and ai's are the parameters of this field. Okay. So now I have got this deformation vector as a function of x, y, z, and it has some parameters a0, a1 and a2. Okay. The next thing that we do is that we say that this u bar or this vector u they should satisfy the boundary conditions. Okay. Or we say that this should be kinematically admissible. Okay, that means whatever the boundary conditions be, those conditions should be met. For instance, in this example, we took this to be the initial field, and then we said that these are the boundary conditions. We applied these boundary conditions, and this field reduced to this expression. Okay, so we made an initial assumption about the field, and then ensured that the boundary conditions are met. Okay, or we assumed, or we made sure that this deformation is kinematically admissible, right, kinematically permissible. Okay. Now once I have assumed u as a function of the phi's, then I can compute my potential energy. Okay, because from u I will get epsilon and I will get sigma, and then I can compute the potential energy. Okay, once I know the expression for the potential energy, then we will make use of the fact that under equilibrium the potential energy should be a minimum, which means that del pi by del ai should be equal to 0, okay, for all ai. Okay, because my this field u, okay, this field u is a function of these ai, aj, ak's, or it consists of terms like a0, a1 and a2. Okay, now these terms a0, a1 and a2, they should be so adjusted that the potential energy should become a minimum. That is why we say that del pi by del ai should be 0 for all ai.
So is it necessary that for equilibrium potential energy should be minimum?
Yeah.
It can be in a state of unstable equilibrium also.
No, we are not concerned with that at the moment. Okay, because when we are talking of finding out the stresses, etc., okay, we will be talking of the case of a stable equilibrium. Okay, and besides, in the Rayleigh-Ritz method, it can be shown that if we go by this approach, okay, and if we follow a certain set methods for choosing the phi i's, we can get a reasonable solution. Okay, if we choose the wrong function over here, okay, then obviously we cannot get the correct solution. Okay, but if we choose this in a systematic manner and so on, then we can get the correct solution for that. Okay, but for equilibrium this condition has to be met. Okay, essentially what we are doing is we have to find out the value of these ai's, and we know the expression for pi. Since we know pi, in order to find the ai's, we will get a system of equations from this, and we will solve those equations simultaneously to get the value of ai. Okay, so that is the basic procedure we are going to follow. Okay, so this is going to give us a system of equations, and this system of equations will be in ai. Okay, so from this we will solve for ai. Once we solve for ai, then we can get the u vector. Once we know u, we can also get epsilon and we can get sigma. Okay, so in this way we will be able to find out the stresses and the strains in the body. We have started with an assumption about the deformation field. We assume that the deformation field is of a particular mathematical nature. Okay, and if that assumption is valid, then we will get an exact solution, otherwise we will get an approximate solution. And one thing that should always be kept in mind, that the finite element method will always give the approximate solution, it never gives the exact solution. Okay, there will always be a certain amount of error in the finite element approach. Okay, any question up to this point?
What is meant by usually kinetically admissible?
The boundary condition should be met.
So then already we are calculating AIs by applying a boundary.
Yeah, but all the AIs will not be found. For instance, in this case, I have applied the boundary condition that at x equal to 0 u should be 0 and at x equal to 2l u should be 0. Okay, but in my earlier assumption there were 3 terms a0, a1 and a2. Okay, now if I consider these 3 terms, I cannot solve for all 3 of them by taking these 2 boundary conditions.
We can apply that the slope in between is 0, in the middle of the slope at x equal to l is 0.
You can apply that, okay, but is that going to be independent? Nevertheless, right now I have taken a simple equation over here, simple expression for u. Okay, this can always be a more complicated thing. Okay, so just by applying the boundary conditions, you cannot solve the problem. Okay, because it's quite straightforward. Irrespective of what the load is, the boundary condition will be the same. Okay, even if I applied a load P equal to 100 newtons, or I apply a load P equal to 1000 newtons, these boundary conditions are going to remain the same. Okay, but the deformation will not be the same. Okay, so obviously if you are doing it correctly, in that case, just by applying the boundary conditions, you should not be able to solve the u vector. It doesn't make sense. Okay, so by applying the boundary conditions, we will be able to simplify this expression, but we will normally not be able to solve it completely. Okay, so we will get an expression like this, and in this case it contains one term a2. Okay, since it contains a2, now we will get the expression for the potential energy in terms of a2, and then apply this condition to get the value of a2. Okay, we will just go through this small example, and then maybe it will become clearer. What we will do is we will take the same example, except for the fact that we will make it a strictly one dimensional case with the loading also in the same direction. Okay, so this is x equal to 0, this is x equal to 2l, and the loading, this loading is P acting at x equal to l. Okay, we will make it a strictly one dimensional case. Okay, now if we say u, that is deformation in the x direction, again we will assume it to be a0 plus a1x plus a2x squared. Again we will say u at x equal to 0 is equal to 0, and u at x equal to 2l will also be equal to 0. Okay, by the same method now we will get u to be what is the expression we had, a2 into x minus 2l. Okay. Okay. Now we have to write an expression for the potential energy of this system. Okay. So potential energy pi, that is equal to half of integral sigma transpose epsilon dV, volume integral of that. Okay, this is the strain energy component plus the work potential, and the work potential in this case, there are no body forces, there are no tractive forces, we only have a point load. Okay, so that will become minus what we have written, sigma ui transpose pi. Okay, since it is again a one dimensional case, sigma will be equal to epsilon times E. Okay, in a one dimensional case, sigma is equal to epsilon into E. Okay, so we will use that over here and we will get half of E, of course, which is a constant, multiplied by, we will get epsilon square. Then we will say that dV will be equal to A times dx. We will assume this rod to be of uniform cross section. Okay, so dV is equal to A times dx, so it will become epsilon squared into A into dx, and it's a volume integral, so it will be integral from x equal to 0 to x equal to 2L. Okay, minus, let us say we will call this point as point number 1. Okay, ui, that means the deformation at this point multiplied by the load at this point. Okay, so the minus u1 into p. Is that okay? Now we will make use of the fact that epsilon is equal to del u by del x. Okay, so our expression for pi will become equal to half E into A into integral of del u by del x whole squared dx minus u1 times p. What is u1? u1 is a deformation at this point. Okay, so if we look at this equation, u1 will be equal to a2 into L into x minus 2L, that is L minus 2L into minus L, so minus a2 L squared. Okay, so it will become, this will become plus a2 L squared times p. Okay, del u by del x, again if you look at this, from this we will get del u by del x will be equal to, this is a2 x squared will become 2 a2 x minus this will become 2 L a2, okay, which will be equal to 2 a2 into x minus L. Is that okay? Okay, simple differentiation. So we'll put that back over here. So we'll get, this would be equal to half of EA into integral, this is from 0 to 2L, from 0 to 2L, del u by del x is 2a2 into x minus L, will become this whole thing squared dx plus a2 L squared p. Okay, we just simplify this and half EA, so this will become 4, this will become 2 EA integral from 0 to 2L
Simplifies to
It should be E.
again.
It should be EA. Okay, it's good. Okay, right.
it's fine.
Anything now?
No.
Okay. Is that all right? What will be this integral?
4 by 3 EA A square L cube.
4 by 3, what is it?
4 by 3 EA
So equal to 4 by 3
EA
EA
A square L cube.
A2 squared
A2 square L cube
L cube
plus A2 L square P.
plus A2 L squared P. Is that okay?
Fine.
So this is the expression for potential energy. Okay. Now we will say del pi by, the only parameter we have here is A2. Okay, so we will say del pi by del A2 should be equal to 0. Okay, which will give us 8 by 3 EA A2 L cube will be equal to minus L squared P. Okay, which means A2 will be equal to 3P by 8 EA L minus. Okay, which means that our deformation U, okay, our deformation U is given by A2x into x minus 2L. So this will become minus 3P by 8 EAL into x minus 2L. So this will be the expression for the deformation. And similarly, if we find out epsilon is equal to del u by del x. Okay, that will be 2a2 into x minus L, that will become minus 3p by 4 EAL into x minus L. Okay, so we have an expression for epsilon as well as an expression for u. If you know epsilon, we also know sigma, as sigma is equal to E times epsilon. Okay, so this is how we can find out all the stresses and strains in the body. Okay, but if you look at this solution, in this solution this deformation u, how does it vary with the distance? Okay, this is x equal to 0 and this is x equal to 2L. This deformation u is equal to 0 at x equal to 0 and is equal to 0 at x equal to 2L. Again,
Maximum at x is
it is maximum at x equal to L. Okay, so it will be maximum some value here at x equal to L, and it is a quadratic relation.
Why should it be 0 at x equal to 0?
Why should it be 0? Because that is a part of the boundary condition. Look at this figure. It is fixed here. There is no deformation here. It is fixed here. There is no deformation here. Okay, that is why we give the boundary condition as at x equal to 0, u is equal to 0. Okay.
What was the
Equation
equation for that?
for?
For u?
This is the equation you have. This equation.
So how come like, from this equation we put x equal to 0? 0.
You have x over here. This is the x.
Okay. I thought-
It's not multiplication, it's an x. Okay, nevertheless. So if x equal to 0, deformation becomes 0. If x equal to 12, this term is 0, so deformation comes here as 0. Okay, if I plot the strains at x equal to 0, it is going to be positive. At x equal to 12, it is going to be negative. And at x equal to L, it is going to be 0. Okay, so the strains would follow a pattern something like this. Okay, well, if you look at this equation, the strain is a linear term. Okay, it is not a quadratic term. Strain is linear. Okay, so this is how the strain would look like. Okay, and this is how the deformation would look like. Okay, but if you look at the actual problem, okay, where we have this rod, okay, and the force acting here, this whole portion is going to have a uniform tensile strain and this whole portion is going to have a uniform compressive strain. Okay, we are not getting that by this method. Okay, we are getting a straight linear variation in strain as well as in stress. Okay, the actual variation would probably look something like this. Okay, this is how the actual strain is going to look, but we are getting a strain which is like this. That is basically because the assumption that we started with, that our deformation u is given by u equal to a0 plus a1x plus a2x squared. This assumption is not correct. Okay, this assumption that the deformation will be a quadratic function is not a correct assumption. Okay, because in this case we know that there will be a discontinuity here. Okay, so we will probably have a different mathematical description for u in this part and in this part. Okay, so since this assumption itself was wrong, we are not getting the correct result, and there is some error between the actual and the result that we have found out. Okay, the finite element method will give us a systematic way of choosing a expression for u and then solving out the system of equations. Okay, so this Rayleigh-Ritz method we are going to use for most of our finite element applications. Okay, so we will start off from this point in the next class. If we have anything, then we will discuss it next time.